Welcome to another exercise in the workbook statistics, this time focusing on the binomial distribution. Let's have a look at the exercise. A train reaches its goal delayed in 25.7% of all cases. In the course of a week, Peter uses the train 9 times. Then our first question is, what is the probability that he will be delayed exactly 2 times? Second, what is the probability that he will be delayed at least once, but at most 8 times? And finally, third, the train makes 480 trips per month. On average, how many of these trips will be delayed? Well, before we can start with any of these parts, let's first discuss why we are actually using the binomial distribution here. On the one hand, we can assume that the probability we have here, so the probability of a delay of 25.7%, this always remains fixed. So if the probability is fixed, if nothing changes independent of how many I observe, then we're always having a binomial distribution. But we can also say, well, if I take a closer look at one train, this does not have any impact on how much delay, how big the chance for a delay for the other trains is. That's just a slightly different reinterpretation of the fixed probability of delay. But this means that we do have a replacement here. So if we select one train, take a look if it's delayed. Doesn't matter if we select another train as well. Even though it doesn't really make sense to assume that Peter goes with exactly the same train twice, or is twice in the same train. But well, even only having a fixed probability like this one here suffices to assume we're working with the binomial distribution. So let's start with the first part of the exercise. So here the question was about exactly 2 times. So we're going to calculate the probability that the random variable is 2. So we have a small k of 2. And we also know the probability, that's the 25.7%. And we know the size of the sample. He uses the train 9 times. So with this information, we can directly use the probability function of the binomial distribution, which in this case would be 9 over 2, so small n over small k, times 0.257, the probability to the power of 2, that's the small k, times 0.743. How do we get this value? Well, this is nothing else than 1 minus the probability. So 1 minus 0.257 to the power of 7. 7 is small n minus small k. So 9 minus 2 giving us the 7. I'm going to put all of this into my calculator, getting a final result of 29.7%. So the chance that his train will be delayed exactly 2 times is roughly slightly more than 29%. Well, that was already the first part. So switching to the second part, part B. Here the question was about, it should actually be somewhere between 1 and 8 times. So well, if it should be between 1 and 8, including 1 and 8, we could calculate all these 8 probabilities. Or we can think, well, what else do we know? We could also consider the counter probability, because here there's only 2 cases not included in this probability. And that's the case that the train is never delayed and that it's always delayed. So the case of 0 and 9. Well, that's much less to actually calculate, and it actually becomes even, or could even become less, if we already had calculated one of these probabilities. In this case, sadly, it's not the case, so we have to calculate 2 probabilities, and we also know, well, similar to the last part, the probability P and the sample size N. With these two, more or less three information, we can again use the probability function of the binomial distribution, giving us here for 0 this part and for 9 that part. That can easily be calculated because these two are 1 and these two are 1. This one and that one. So summarizing all of this, we will get a final result of 93.1%. So the chance that the train is at least once, but at most 8 times delayed, so somewhere between 1 and 8 times, is slightly above 93%. Well, that was already then as well part B. So let's turn to the third and final part, to part C. In part C, we're actually looking for the arithmetic mean. Well, the arithmetic mean in this case can easily be calculated as the sample size times the probability. However, we need to consider here we have a slightly larger sample size. We have 480. So we're using the 480 and we're using the probability of delay. Multiply both of them and get as a result 123.36. So somewhere between 123 and 124 trains will be delayed on an average month. Well, that was then everything there is to this exercise. I hope you enjoyed it. I say goodbye and see you next time.